This is problem 2 on exam 2 in module 2, which is on page 50 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 2 is some number of electrons are removed from a thin aluminum disk that has a radius of 25 centimeters. A proton is released from the center of the disk at rest. It accelerates away from the disk, reaching a speed of 100,000 meters per second after traveling only 1 centimeter. How many electrons were removed from the disk? If you remove electrons from the disk, it'll be positive. It'll push a proton away because a proton's positive. Makes sense? Let's draw a diagram. Here's the disk. There's the proton right here. Not to scale, of course. We suck electrons off the disk. We release the proton. It goes from 0 to 100,000 meters per second in 1 centimeter. There's the field lines pushing the proton away. What's our strategy? Well, let's think. We know it goes from 0 to 100,000 meters per second in 1 centimeter. It seems like we can get the acceleration using kinematics. If we get the acceleration, we can get the force from F equals ma. If we know the force, we can get the field from F equals QE. From the field, we can get the charge on the plate. And from the charge on the plate, we can get how many electrons were removed. It's a multiple step problem, but looks like we can do it. So what's the acceleration? We can use an equation, but let's think. Try to follow along. Slowly, carefully, pause if you need to. The force is constant, the acceleration is going to be constant. The field lines do not separate when you're close to the plate. The field's constant when you're close to the plate. Acceleration is constant. It goes from 0 to 100,000 meters per second, so the average speed is 50,000 meters per second. If it averages 50,000 meters per second, it'll take 1/50,000th of a second to travel 1 meter, and 1/100th of that to travel 1 centimeter. So it'll take 1/5,000,000th of a second to travel 1 centimeter. That's the time. The time is 1/5,000,000th of a second. And it goes from rest to 100,000 meters per second in a time of 1/5,000,000th of a second. The acceleration is 5 times 10 to the 11th meters per second squared. That's the final speed. Starts at rest. That's the time. That's the acceleration. All right, I know you want to do it with the equation. Here's an equation. V final squared equals V initial squared plus 2ax. V initial 0. V final is 100,000 meters per second. 2ax, we put x, 1 centimeter, in units of millimeters. And we can solve for a. And it's 5 times 10 to the 11th meters per second squared. With the acceleration, we can get the force. F is ma. The mass of the proton, 1.67 times 10 to the minus 27 kilograms. Force, 8.35 times 10 to the minus 16th newtons. Now, from the force, we can get the charge. We can get the field. We know the charge. It's 1 electron. It's the electronic charge because it's a proton. 8.35 times 10 to the minus 16th newtons. There's the charge on the proton. We can get the field. Field is 5,220 newtons every coulomb. Now we can use Gauss's law to get the charge on the plate. We know what the field is. E dot A is 4 pi kq enclosed. We have to choose a good Gaussian surface. A nice cylindrical pouch that fits snugly right around the whole plate. There's field lines on both sides of the plate. They cover the entire area of the plate like that. Gaussian surface is this. The dashed cylinder snugly around the plate. There are edge effects. If I stick a proton right here, it's going to accelerate away. There's the field lines at the edge. But it says it's a thin disk The charge on the curved surface will be small, and the area of the curved surface would be small. So we could ignore it. Remember, these are two disks. If I turn these things sideways, you'll see the area is huge compared to the edge. So the area through which the field lines are penetrating, which is the flat disk, the two circles, is pi r squared times 2. That's the area. Radius is given, 25 centimeters, 0.25 meters. Gauss's law, E dot A is 4 pi kq enclosed. We can stick in the numbers. We already calculated E to be 5220. We can plug it in, converting the centimeters to meters right here before we punch in the numbers. And we get 18.1 times 10 to the minus 9th coulombs, which is 18.1 nanocoulombs. But that's not the answer. How many electrons were removed from the disk? Q enclosed is the charge on the plate because the Gaussian surface has the whole plate. So there's the total charge. There's the charge on one electron. We multiply the electronic charge by n, the number of electrons, and we get the total charge. And we get 1.13 times 10 to the 11th, which is 113 billion. 113 billion electrons were removed from the plate. That's problem 2 on exam 2 in module 2.